Okay, hello, I'm Nick, and in this presentation, I'm going to give you an idea of the bring up process or the challenges of bare metal, and I'll start with some horror stories from previous projects and current projects. I won't name them. When you get a new system, and either if even in its design phase before it reaches tape out or becomes an ASIC, there are a lot of hardware bugs that are there, and it's not just hardware bugs. From the system software perspective, you have a tool chain, you have a software stack, and this software stack expects some bare minimum functionality. Okay. Um, initially, while the hardware team is working, some of that functionality may not be available to you. An FPU, for example, is an example, although it's not uh, really, you don't really depend on it. But maybe your software stack does, or maybe you need a timer, you don't have a timer, or maybe you need a way to handle interrupts and you don't have an interrupt controller. So you need to you start you need something more flexible. And then you have all these upcoming issues that you may find. Here I have a list of some of the issues we have dealt with, like in case of RISC-V implementations, we've seen from issues with compressed instructions that couldn't work in properly, that because it's a shorter instruction size. They had issues with alignment. We had issues with atomics and alignment. We had misbehaved MMUs. MMUs are hard to validate, or a non-compliant VPU, also buggy. Maybe transaction would stall, the core will hang because of the VPU. We had a misbehaving branch predictor that was very nasty. It was on Ariane. We submitted a fix for it. So basically, you are running your software and you get a crash, and the crash, the address in the crash is from machine mode. It's not even, you're on Linux, for example, and you see a crash and the address is not even a virtual address. That's because the branch predictor would do stuff while you were on Linux and could crash. Other stuff, like a recent bug I found, is a non-compliant wait for interrupt instruction that increased the program counter further than it was supposed to. In general, sky is the limit. We've seen so many use cases, so many issues here. And it's part of the process, right? We are working with experimental hardware. We'll end up having hardware bugs, and we'll have to figure them out in the software and deal with them. And there are also other issues regarding while we progress through the development process. During integration, for example, there was an issue when we had mixed up the interrupt lines. I would expect the timer interrupt to be in wire one, and it was in wire, I don't know, three, or the hearts, the interrupts that were directed to hearts were connected mirrored. So I would wake up heart zero and I was waking up heart four, stuff like that. But and keeps bugs keep coming up, and so even after this process that you've identified issues in your FPGA designs and you have resolved them, then you move to ASIC. And there was a bug in the tool chain that took out our network on chip. It was optimized because it wasn't connecting anywhere. The tool chain thought, okay, let me throw this out, and suddenly we don't have any DRAM to play with. And even at the PCB level, I mean, after you've done everything, maybe your board also has issues. Okay, maybe your board. I had an issue with QFDB. That's one of the images you see on the right. Where DRAM lines were not connected properly, or the storage, the NVMe was looking towards the outside of the board, and you have to deal with this stuff. And to come to our issue here, to our subject, these issues survive the hardware validation and verification process. If we have to deal with it, if the software people have to deal with these issues, that means these issues went through the whole validation and verification process in hardware. So they're not easy to spot, okay? They're not trivial. They're more complicated things that you need to worry about. And the longer they survive, the harder it gets to fix them, and the cost of fixing and dealing with them grows exponentially. I have this illustration here. We have some similar illustrations in the security world, by the way, when we talk to our clients about the software development cycle and the secure software development cycle. We tell them that if you let a bug if you let a bug propagate, it will the cost of your bag would grow exponentially. When in hardware, that's really true, and it's even more, serious after tape out, because after tape out, there are no bug fixes. You are stuck with it, and not even post silicon also. I mean, but tape out is like too much. And when it goes to the field, when this goes in production, then there is no way back. I mean, so you need to catch those bugs early on and fix them, because then you have to maintain a weird uh, software stack that is patched all the way. You can see on Linux, for example, that we have such cases of platforms. For example, the T-head SoC has a serious issue with its CPU. You can find the CV online where you can access the whole physical memory because of it. Or it has a non-compliant VPU. There are other boards that had a non-compliant MMU, for example, and Linux said, okay, I give up. I won't support those boards. Um, so you have if this reaches production, if this goes outside, you'll have to maintain the software yourself or try to deal with this in a way. So how do we deal with this? We need more tests, and we need lots of tests, and we need tests that we can run as early as possible during the development process. So even before extensions are ready, even before IPs are ready, the moment you have something that can run code, you need to have a test for it. Uh, so and it should grow progressively, become more complex as long as much as you're getting more IPs there, your system becomes more complicated, you get more functionality. So your test coverage will also increase. Now you have one core, then you have multiple cores. When you have multiple cores, you also have to deal with a cache subsystem and deal the memory sub and try play with the memory subsystem, stress it. Uh, you have interrupt controllers, you have peripherals. You need to test the whole thing. And for this to work, you also need to help. If you want to catch bugs early on, you also need to write very small and efficient tests so that maybe the hardware people can run them in simulation. Simulation takes a lot of time, and you don't want to run a full-blown software stack in node simulation, because it will take days, maybe. So if you want to spot specific bugs, it's better to have specific tests for those so that the hardware team can replicate them. Although we didn't have DRAM in that PCB, you need tests that would allow you to salvage what you can, meaning that, okay, this didn't work, but what did work? I need to have, because if we are respinning the board, or if we are respinning the ASIC, we need to know what we did correct, or what didn't, or what other things failed. Because you see the board, you say, okay, it doesn't have any DRAM, so game over. It's not game over. Maybe something else is also wrong, and you also need to figure it out before you go for a respin, or else you need a second respin. So you need to salvage what you can, meaning that your software needs to be able to run in a very constrained environment, for example, in an environment without memory, or where the memory is your cache acts as a scratchpad, for example. You only have a couple of kilobytes of memory, or that you have to come up with a backup plan for this. So it's a challenge. And we had multiple small tests that we were playing with. And at some point, I thought, because again, I'm a bit lazy, I don't want to rewrite things from scratch. I wanted to have an infrastructure to write. To help me in writing such tests and help my colleagues also write tests. So I started with writing something like an SDK or a framework, you may call it. And initially it was for tests, but then I started playing with it more, and I also use it for benchmarks. We also use it for education, because it seemed like a good way to showcase to students how bare metal programming works, and tell them about the linker, about the memory layout, about all sorts of things that happen like under the hood. And also I also use it for as a boot ROM or for bootloaders. I show you a demo later on. Um, so here's how it evolved. I started it in 2019 as a side project. And I plan to release it under Apache 2. I think we have a release in the Riser GitLab, but I want to make it more public. It's still not there. I'm a bit of a perfectionist. I don't know. I don't like it yet, but I will release it. So it has two layers. It has a platform layer. The platform layer deals with platform-specific code. It supports standard RISC-V ISA extensions. It also supports some standard peripherals that are, by the way, mandated in the RVA profiles. So if you see the RBA 23 profile, it says you need to have a UART and you need to have an internet controller. So these are peripherals that are RISC-V specific, and they're expected to be in a standard RISC-V SoC. And those are enough to have a full SoC, by the way. I mean, have a lot of functionality there. Um, so I want to add support for all of them. Currently, I have the basic support. You can support multiple cards. You can have sparse hard IDs, meaning that they can come up in any order they want, or maybe a hard doesn't come up. This is something that's really a requirement also in production when some of the cores in your chiplet or your chip they didn't come up properly, and you still want to use the rest of them. And it can support complex memory layouts. So one of the issues we have is that we don't want to be constrained on where we put the boot ROM or the ROM of that RAM that contains the bare metal code and RAM. And those may be very far apart. And when they are far apart, the PC relative addressing of RISC-V doesn't work. And you need to go with either GP relative or go for the large memory model. The large memory model has brings some baggage, and also it's not supported for previous tool chains, and it's not yet standardized. So I have a hack there that allows you to do that with GP relative, but with some constraints that I deal with them with the linker script. And I try to have the whole description of the hardware in one header. You see an example on the right. So once we have a new target, a new platform, a new SoC or board, we just need to write a header file, and the code will adapt to it. And I also have support for the QEMU virt machine. So when this tool you compile things, it gives you two binaries. One is the one you can run on your platform, and the other one you can run on QEMU. And this is to validate the behavior in both of them. So it's the same code you wrote, and you can test it on QEMU and then test it on your platform. And if your platform doesn't follow, you probably did something wrong. Um, so yet another way of catching issues. YaLibC is the libc layer of this. So it's a generic code. It's an attempt for a freestanding libc. That was another side project of mine. It's very minimal. I just put there only what's needed. But why did I do this? Because the available libcs out there, they're not freestanding. They are hosted. Even new libc and Pico libc, they require the hosting environment, or at least some. They are not true freestanding. They have things that they don't make sense in bare metal. And because I wanted to have fun with it, so so the work in progress. The platform layer already contains the old school, old interrupt controller thing. Now I'm adding AIA support. That's the new advanced interrupt architecture. I'll start with, I already have ACLINT. It's the advanced CLINT. It's the core local interrupt controller. I'm adding the platform level interrupt controller, the new one. And then I'm going for IMSIC and uplink. IMSIC is the new way of handling MSIs on RISC-V. And I'll add ePMP support. That's because I also want to have some security in there and isolate the stack from the heap or the code, not being able to execute memory, stuff like that. In YaLibC, I'm trying to I try to add more functionality and keep it like C11 compliant. I want to skip, for example, right now I have a nanosleep. Nanosleep is not part of C11, it's part of POSIX. I need to use another one. I want to get rid of preprocessor macros and use linker aliases. This is a trick I want to do so that you don't have to recompile the libc view. For example, you don't want the full printf, or you want a limited version of some function there. I instead want you to. I instead would compile everything and at link time, I'd give the opportunity to the user of the library to pick the version using linker aliases. So you have let's say a symbol alias that's called printf, and it points to either the full implementation or the simple implementation. and that happens at link time, and then LTO will come on and clean it up. So you end up only with with a simple one in your binary, and you don't do this at compile time, or you do this at link time. Um, it has some pros and cons this, but I wanted to play with it, and I have an idea of how this can be used in the future. So. And I'm still cleaning things up. As I told you, I want to release this at some point. And the future work, after I've added AIA and the rest of the stuff, I want to add more infrastructure for running things on S mode with virtual memory. Currently, you can run code on S mode or U mode for deprivileging your payloads, but I want to add them to run them with virtual memory and possibly with an IMMU support so that I can talk to peripherals, so that I can share the page table with peripherals. This may also cover the use case where I want to use this SDK for running payloads for accelerators. So that you want to offload something to an accelerator and you want this is a use case that's coming up now because people want to run very efficient payloads and accelerators that without bringing the whole OS in there. You may look at unikernels and how they are playing with it. Bare metal is kind of it's like the next evolution of that. So again, adding more tests. I want to have a profiling suite for hearts. I'm working on it, and maybe other RISC-V extension and non-ISA extensions, meaning that non-ISA means IOPMP, IOMPT. It's the things that are used by COVOR, by platform security. We're gonna use that for when creating for example, a security engine or a security microcontroller as part of a boot of a board level controller. So this is a use case example. As I told you, I've been using this for all sorts of things now. One of the use cases I have here is a bootloader, but it's a zero-stage bootloader. So it's bootrom is the first thing that the core executes when it comes out of reset. And in this case, it gets its boot images from network. So this is a very useful feature because in prototypes we usually don't have storage. When you get an FPGA card, it doesn't have. It has a flash, but it's for the bitstream. It may have an SD or may not, but it always has either an Ethernet, either an RJ45 or an SP or an SFP connector. So you can get networking there earlier than getting storage. Also, SD or F or these kinds of flashes are very slow, so and not very big. So you could put your boot images there, but not the whole OS. So you still need to get the rootfs from somewhere. And when you have network, you can get all of them from network, meaning you can get your boot images from network. You can also get your rootfs over NFS. So way more flexible. Now, of course, we have some setups that we have NVMe there. I mean, in Riser, we are aiming for cloud setups, but still, this is a good use case, especially when you develop things, because you don't want to always flash your new boot images that you create. So you just compile them, and then the board comes and takes them from the network through the network instead of you having to continuously swap SD cards or reflash the flash. So what it includes, it can be used in various use cases. One is the prototype, but this could easily be used in production as well. I mean, there are boards that are there that do this, especially embedded boards, or your VoIP phone in your desk does this when it boots. And also in the security controller, that's why I told you I want to add IOPMP and other stuff like that. That may also fetch images from the network. So currently it has an Ethernet. The stack is very simple. It has an Ethernet driver. I have like 3 Ethernet drivers supported there. Virta.ionet is for QEMU, IMAP Lite, and Carve and our own Ethernet DMAs for our prototypes. But it's easy to add another Ethernet driver there. It has a tiny network stack like for it has IPv4, ARP, and UDP support. Nothing crazy there. No IPv6, not other fragmentation, no such thing, not or jumbo frames. A very simple network stack. It has a decent DHCP client. Actually, the DHCP client is fully featured. It supports options, lots of them. I mean, it's a good one. And it's above all was very strict with protocol behavior there. And the TFTP client, which again, it's this one is stack only, it doesn't need any memory allocation, and it supports block size and window size options. This allows you to be very efficient. It allows you to bring, so the default block size of TFTP is 512. This allows you to go like the full MTU, and window size allows you to do selective ACK. So you acknowledge a window instead of acknowledge every packet. Again, more efficiency, and more efficiency in this case means you boot faster. So the whole thing is 19K right now, which is okay. I believe I can make it smaller, but I think it's a good one. I couldn't do this if I went for a more, complex stack or a more complex C library. And what this thing, the images it fetches, I can also simplify this. So, for example, this is a standard boot flow from Linux. You start from boot ROM, and the boot ROM has the device tree and the firmware image, and then the firmware image will need to get the second stage bootloader or the OS image. And in our case, we've combined all of these boot images, the secondary images in one, and the device tree. So we have two images. So it's much more simpler. And you only have to fetch two images, and then one of them will be OpenSBI. It will include the kernel, and then you will either get the user space from NFS or be there. I want to improve this. I want to have a unified image format, and I also want to add secure boot in the mix. Initially with Calyptra, meaning that I won't do the crypto myself. I will use a root of trust, an external module to do it for me, and or a software as a feedback, as a fallback in case we don't have an external RTM. I will have baked public keys in there and craft a software TPM. Um, I want to be able to support the flash storage, but I don't want to go, weird stuff. So I go with JEDEC compliant SPI nor flashes. They have a common programming interface, and eMMC again. The commands are straightforward. So this would be optional. You would be able to choose one or the other, but I want them so that it's not just netboot, it's a full-featured boot ROM. And my target binary size is 32 kilobytes max in the case of the external TPM or RTM, because if the software RTM, meaning doing crypto in software, it will take more than that. But I guess I can do it in less than 64K, I guess. The memory I use, it depends on the Ethernet driver, on the platform, but it's very low, and I can keep it very low because it's mostly stack allocations. I have a heap allocator there so that I have, because of this issue I had with PC relative, so that my data segment cannot go longer than 4K. But yeah, it's really very compact, so it can run in very constrained environments, even in environments when you don't have RAM, for example, and you want to fetch tests and you want to do stuff. So it also works as a gateway for fetching tests for the platform. Thank you.